Hi everyone, my name is Somaya Sadat. I'm the Assistant Director at the Center for Analytics and AI Engineering at the University of Toronto. It's my pleasure today to welcome you to this joint seminar with the University of Seoul on the role of ontologies in smart cities. Our speaker today is Professor Mark Fox. Dr. Fox is a distinguished professor of urban systems engineering, professor of industrial engineering and computer science, director of the Urban Data Center in the School of Cities, and founding director of the Center for Social Services Engineering at the University of Toronto. Dr. Fox pioneered the field of constraint-directed scheduling and the development of ontologies for modeling enterprises. He's currently investigating the application of ontologies to the representation and utilization of urban knowledge, including social services, transportation, and water and sanitation. He's actively involved in the development of international standard city data based on his urban ontology research, including ISO IEC 21972 upper-level ontology for smart city indicators, and the ISO IEC 50787 series of city data model standards. Dr. Fox is also an entrepreneur, having co-founded Carnegie Group Inc. in 1984, a software company that is specialized in artificial intelligence-based systems. With this brief introduction, I'd like to give the floor to Professor Fox for his presentation. And as mentioned in the chat, please feel free to type in your questions in the Q&A box, and Professor Fox will try to answer them at the end of the seminar. Thank you.
Thank you very much, Somaya. Can you hear me?
Yes.
Okay, terrific. So let's start. Thank you, everybody in Seoul, for joining us today. It is morning there, evening here, obviously. What I'm going to do is talk about ontologies, okay? And it's sort of, strange to talk about ontologies, which is a branch of AI. It's tends to be called knowledge representation of reasoning, when we live in a time where machine learning and neural nets are consuming all of the oxygen in the room. And with the advent of ChatGPT and similar technologies capturing everybody's attention, why should we be concerned with ontologies and knowledge representation? Well, let's consider the following example. Imagine you're a city, and what you want to do is you want to pave a road. And all of us have had the experience of driving down a street or walking down the street and seeing a road being paved, and then seeing it being paved 4 or 5 months later again, and dug up and then paved again, dug up and paved again. And you sort of wonder, why can't they get their act together? Why can't they figure out, just dig up once, do whatever changes you need to make, and then pave it again, pave it once? This issue is common across cities, across the world, and it stems from some very basic issues. So if you're going to pave a road, what a city usually does is they'll put out a tender or a call for proposals, which contractors will respond to. But if they are going to pave that road, if they're going to pave the road, then before they pave it, they'll actually, or should, communicate with the water department and ask the question, or tell them, we are going to pave this road. Is there anything that needs to be done underground? Not only should they be doing that with the water department, but the sewage department, asking them, when you pave a road, should anything be done underground? And the same with electrical power, and also with the permits department. And what I mean by here is that if you're going to dig up and then pave a road, have you already put out permits or accepted or given permits for a parade or some type of demonstration or whatever the case may be that's going to occur on that road? It gets more complicated. in that you need to interact with the police in order to make sure that everything is cordoned off, barriers are put up, etc. You need to coordinate with the transportation department to make sure that any buses or other types of transportation are redirected. And you need to coordinate with the businesses that are on that street to make sure they're aware that this work is going to be done and it will possibly interrupt their business, if not even close it down in a sense. So the point being that paving a road is not simply finding a contractor who's going to pave it. It's really a problem of coordination and cooperative problem solving amongst the various different departments and divisions of a city so that they are not only aware, but can rearrange the work that they want to do at the time the road is being dug up and then paved. So for example, from a cooperative problem solving point of view, it may be the case that the water department has planned to replace the water pipe under the road, but not for another 2 years. But given the opportunity that the road is going to be dug up and then paved, they may move that forward. And the same would be with sewage, and the same would be with power. Power may say, maybe we should, when it's dug up, put more power lines underneath, increase the electrical capacity, given we're moving into an electric vehicle world. And so it's all about coordination. It's all about cooperative problem solving in order for tasks within the city like this to be successfully performed. So what does that say about the dream of smart cities? It says that if we want to achieve smart cities, that is achieving an efficient, sustainable, resilient, and citizen-centric city, we need to be making better decisions using technology such as AI, statistics, operations, research, etc. But these decision support and decision-making technologies have to rely upon sourcing and integrating data from across the city, and requires the capability to coordinate planning and operations across city divisions and external stakeholders. So the bottom line is the key to making cities smarter in the end has to do with cooperation and decision-making, cooperation of the different departments and divisions, making decisions cooperatively, sharing information amongst the different divisions. And what are we doing about that? How are we approaching smart cities today? Well, we're doing smart streetlights. We're doing smart garbage cans. Garbage can signals when it's full, needs to be emptied. Smart lights determine when to go on and off and whether there's traffic or people or not. Smart fountains, smart traffic lights that look at what the traffic is going in, perhaps even looks further down the road to see what traffic is coming its way. All of these smart city applications can be viewed as operating at the margin, at the edge of what goes on within a city. They are low-hanging fruit, if you will, of applications that are easily implemented and don't change the basic nature of the city, does not change the basic operations of the city. And what I mean by that is, doesn't change the education system, the transportation system, water and sewage, social services, public health, public safety, fire and emergency, parks and recreation, housing, etc. And if you look at a budget for a city, there are billions and billions of dollars being spent in these areas, and the smart city applications we saw earlier represent only a small fraction of where money is spent. So the problem that we have here is if we want to make the transition to a smart city, we have to look across these different silos and ask the question, given these silos, these different departments that operate semi-independent of each other, how are we going to get to the point where they are cooperating in the solving of city problems and they're sharing data in order to make better decisions? Now, that's the ideal. The divisions cooperating with each other and solving problems, delivering services within the city, sharing data, etc. We'd like to achieve that, but there are going to be problems with achieving it. And the problem, or what I refer to here as organization obstacles to SMART, have been around for a long time. The first obstacle that exists to change, that is the obstacle to transitioning to a more smarter city, is that every organization has a structure. This is the organization chart for the city of Toronto. Each one of these areas here represent separate different divisions of the city. And the fact that these divisions exist, these boxes exist, the boundaries exist that we see here, means that by definition, these departments are separate from each other, and that separation hinders cooperation and coordination. And that's the nature of organizations. Once you create an organization structure, you are imposing separation between different people, between different departments, etc. And it cannot be easily changed because this organization structure in turn affects the way people think, the way they work with other people, the way they behave, etc. And even more so, these organization structures have evolved over decades, if not centuries, to the point that even the vocabularies, the words they use to talk about their particular area, whether it be water or sewage, parks and recreation, public health, etc., they use a different language and they don't necessarily understand each other. So if we are to change in the direction of a smarter city with better cooperation, coordination, sharing of information, it's easy to change the diagram. It's going to be more difficult to change the people and the systems that underlie it. A second obstacle to change is a lack of shared data. So, as I said, the structure of municipal organizations directly influence the information systems and software applications. And as I said, each division, each department, etc., develop its own language with which to talk about what they do. And because they have their own language with which to talk about what they do, it becomes difficult to share data because that language then impacts the data models of the information systems that they use within a department, within a division, has a data model that encodes that language, that specific language. And if you wanted to change all the information systems so that they had one single data model that's shared across them, you would have to redo decades and billions of dollars of investment in those systems. Now, the core problem of lack of a shared data model is the problem of semantic interoperability, or the lack of semantic interoperability. And semantic interoperability is the ability of computer systems to exchange data with unambiguous shared meaning. Let me give you a very simple example. Let's say it's the Department of Water and Sanitation, and they refer to something called a plant. When they think about that, they're talking about some type of plant that does water processing or sewage processing, etc. But if you're dealing with Parks and Recreation and they refer to a plant, they are referring to this green leafy thing. So the languages are different. The semantic interpretation of the terms that are being used in the data models differ. And if we want to achieve some level of cooperation and coordination, we need to address this basic issue of semantic interoperability. A third obstacle to change are privacy constraints. Okay, so again, we have this diagram of the different departments, divisions, et cetera, of a city. We have this desire to achieve some level of cooperation and coordination. We have this desire to share data across the different departments and divisions. But a major obstacle today is the introduction of privacy laws. Now, why do we have privacy laws? We all understand why. We want to protect data about individuals. And the problem in cities is we're not talking about privacy of data in data sets where you want to de-identify information in the data set. We're talking about data about individuals that's necessary for the functioning of the city. If we want to provide housing to a household, to a family, we have to know who the family is. We have to know the members of that family. We have to know what their income is. So for the successful operation of many of the services that the city provides, it is necessary that access be provided to specific information about specific individuals, households, etc. So access to identifiable data is absolutely necessary to the operations of a city. But we have this problem, and that is, given privacy rules, the knee-jerk reaction to a request for data about individuals from one department to another is to say no. To say that privacy laws do not allow me to share this information that I have about an individual to anyone else, which is just basically wrong. So that's an obstacle to change also. So how can a city become smarter when the organization is designed to hinder it? What I'm going to do is I'm going to give you three pieces or three steps in a recipe for change. The first is identifying key business processes. Okay, so if we want to achieve high levels of cooperation and coordination, if we want to achieve the sharing of data necessary for that coordination and cooperation, then we can't just simply say to all the departments and divisions, share all the data that you have, regardless of what it is. You have to take another approach, because privacy does become a concern if you were going to say all the data should be available to every department within the city. So the first thing you have to do is identify the key business processes in the city. A city has business processes. It has processes with which it delivers services. And what you need to be able to do is identify what those processes are, who the departments, divisions, et cetera, are that are participating in those processes, and then identify for each process the minimum viable data that needs to be shared for the successful implementation and operation of the process. So we're not talking about sharing all the data that everybody has. We're only talking about identifying what the minimum amount of data is that needs to be shared for the specific purpose of that process. And then we go ahead and focus on the standardization of that data. We create a standard with which to represent that data so that data can be shared and understood by all of the participating departments, divisions within that process. Let me give you a quick example of that. The example is taken from human services within the city of Toronto. So my group works with the city of Toronto on the problem of shared data across its different divisions and departments. One of the parts of the city we work with is human services, which is responsible for providing social services to both individuals and households within the city. And the types of things they do is address the issue of the needs of housing, food, training, home care, getting transportation, electricity subsidies, etc. And what's interesting about these questions that would be asked by a citizen to the city is they span many of the services / departments that exist within the city. So the Human Services Department needs to be able to interact with the different departments and divisions in order to identify how best to provide services to the citizen. Now, given the approach that I mentioned earlier, the first step is, what is the process? So for example, the business process we're looking at in this case is homeless person housing. And so one goes through this effort of mapping the business process. What are the different steps, the tasks that are performed, and who are the different departments and divisions that are performing these tasks? So in order to maximize services to the citizen, we have to share citizen data across services provided by different divisions and perhaps at different levels of the government and the private sector. And within the city of Toronto, some of these tasks, and I've simplified this diagram accordingly, some of these tasks are actually performed by the province as opposed to the city. And some of these tasks are performed by external organizations, whether it be an NGO, a charity, or whatever the case may be, that specialize perhaps in training and other things. So what we see just for dealing with homeless people, we have to be communicating with shelter services, with housing services, perhaps public safety, et cetera, to understand, to get the appropriate information and to coordinate the delivery of the service to them. Once the process is identified, then you can go ahead and start analyzing what the minimum viable data is. And so what we see here, and you don't really have to understand the details in any way, is that in the blue, and what we're looking at here is a process from 311, which is the call center for the city of Toronto. What we're looking at here, service requests, request types, customers, et cetera, is data unique to that particular process of dealing with customer queries or requests. And what's in black are entities and attributes, et cetera, that are common across multiple processes. So if we look at a second process, such as the shelter example we were dealing with, there are entities and attributes that are specific to the shelter process that needs to be shared. And there are entities and attributes that are commonly found across many different processes. So our task is, can we go and identify the data that needs to be shared across a process? That's step number one. And when you look at multiple processes, can we identify what is core, that is, what is common across the data that is being shared across multiple processes? And hence we have a core data model and then extensions to it for the different processes. Third, we then deal with the issue of privacy by defining process-based privacy, where participants in a process commit to providing and using data required for the intended purposes of the process. And so what we do is we get the different departments, divisions participating in a particular business process to sign on to the fact that they are participating in that process and they're providing data specifically for the purposes of that process. So everything up to this point is focused on what the problem is, sharing data, what the obstacles are, the organization structure, semantic interoperability, privacy, and what you can do to address those obstacles within the context of the city. Now what I'm going to do is drill deeper into one aspect of what I've just discussed, and that is specifically the underlying data model that would be shared across the departments, divisions, etc., that are participating in a particular process. And that's where the term ontology comes into play. Because as I said earlier, we have this problem of semantic interoperability. We have the problem of developing a shared meaning across divisions, a shared interpretation across divisions, in order to have this shared data model. So what is an ontology, or sometimes referred to as an applied ontology? And this is really, really important to understand what's involved in the building of ontologies. An ontology attempts to answer the following questions. Number one, what are the core concepts and properties that span the domain's data? Now, this notion of core concepts and properties is common to any data modeling effort. But what begins to distinguish what you do in ontology engineering is we ask the question, to what extent can we generalize them in a useful way so that these core concepts and properties apply across multiple processes, across multiple divisions, etc. The second question that we attempt to answer is, what are the key distinctions? How does a particular concept distinguish itself from another? What is the key distinctions between a plant that is a green leafy thing versus a water processing plant? What's the distinction between a resident or a non-resident of the city? Can we formally define the necessary and or sufficient conditions for something to be an example of a concept, to be a member of that concept? That's what we are concerned with when we develop ontologies. So an ontology, it turns out, is more than a reference model or a vocabulary for a domain. It is a precise, formal, logical language, usually, representation of the meaning of concepts and properties. Okay, let's look at an example of an ontology or a piece of an ontology. Consider the domain of transportation planning. Transportation planning predicts the demand for transportation over a multi-decade horizon. But in order to do that prediction, it has to forecast how the city is going to change over the next 20 or 30 years. And in particular, it has to be able to forecast what the demand is going to be for transportation based upon how the population of the city changes over time. And the way transportation planning approaches the forecasting of population is to identify what are called households and their members. So a household could be a family with a mother and a father and 3 kids, or it could be a single parent family, or it could be a senior living alone. There's a variety of different types of households. And what you want to do is first understand, one, who are the members and what are their transportation requirements going to be? And for example, you could have students and they need transportation to go to school. You could have parents who are working, they need transportation to go somewhere else in the city to work. You may have a senior citizen that needs to go to some type of senior activities elsewhere in the city. And what you want to know is how these households change over time. People are born, people are passed away, families are divorced, et cetera, et cetera. And so you want to see how these households change, grow, get smaller, et cetera, et cetera. You want to deal with immigration into the city. All of that has to be taken into account in order to understand after 10 years what the households look like, after 20, after 30, et cetera. So that's the problem, transportation planning. Within the context of transportation planning, I want to convey to you what are the ontology components. When I think about ontologies, I think about three levels of an ontology. The bottommost level is what we refer to as a knowledge graph. A knowledge graph is basically a network of nodes and arcs. And these nodes can represent classes or concepts such as person, household, resident, building, etc. And these arcs can be properties. But the other interesting thing about a knowledge graph is that the nodes can also be instances of these classes. So if these nodes are things like residents, households, members, transportation network, vehicles, etc., then these instances are instances of these classes, an instance of a vehicle, an instance of a household. And so a knowledge graph contains both, in essence, the data model, the ontology, and the instantiation of that data model for a particular application. The next level of an ontology is what we refer to as the definitions and constraints. Most people today, when they talk about ontologies, tend to be talking about knowledge graphs. But what sets ontologies apart is not just the graph structure, but the fact that the ontology also contains definitions for the classes and properties, and also contains constraints on the interpretation of these classes and properties. And it's through the use of these definitions and constraints that we can actually achieve semantic interoperability. If you just have the knowledge graph and you just assert, here are the classes properties that we're going to use in our application, you are basically attempting to achieve interoperability by fiat, by saying, here's what we're going to use from a knowledge graph perspective, use it. Whereas when you go to the next level in providing definitions and constraints on the classes and properties, etc., then you're moving towards semantic interoperability because you're providing an explicit representation of what the meaning is of the classes and their properties. So for example, if you want to define a resident, a Toronto resident, you need to be able to represent the definition, which is resides in, owns property, or owns or operates a business in Toronto. If you want to represent the definition of a household, you need to represent household is composed of at least one person who resides at the same address. So the point is, in an ontology, we take these textual definitions and we translate it into a logical statement that can be explicitly represented and reasoned about, and also represented within the knowledge graph itself. So the knowledge graph contains both, well, three things: the classes and properties, it contains the instances, and it contains the definitions and constraints on these classes and properties. The third level of an ontology is what we refer to as a microtheory, which is basically a fancy way of saying a set of rules or axioms that allow for certain types of deductions. For example, we may have a rule that says for each year above the age of 14, a member of a household will leave with some probability based upon the age. This rule allows us to then forecast how a household changes over time. Let me give you an example of a city resident. So as you know, cities provide many services to their resident, but in order to receive those services, you have to be a valid resident of the city. For example, free transportation may be provided for senior residents. So possible uses of an ontological description of a city resident includes verifying that a person who requests a service is a resident, given a database of people, determining who are residents of the city, validating manual classifications of residency, and inferring characteristics of residents. So if you're a resident, then your address, your household address, excuse me, will be within the city. So the question is, how would an ontology help? Well, first we have to face the problem, the following problem. There is no single definition of a city resident that applies across all cities. Here are the definitions of a city resident from 4 different cities, actually 3 cities in a country. Toronto is, you are identified as a resident if you reside in, own property, or own or operate a business in Toronto. Beijing, it's all individuals holding the nationality of the People's Republic of China who have a domicile in Beijing and nowhere else, et cetera, et cetera. New York is the place in which individual intends to be his permanent home, the place to which he intends to return, et cetera, et cetera. So each city or country has a different definition for who is a resident of the city. So we can't just simply say, here's the definition of a resident in a city. We have to have a more nuanced approach to representing the notion of residency. So here is a knowledge graph for representing a Toronto resident. You're identified as a resident, so you're a Toronto resident. If you own property in Toronto, reside in Toronto, or operate a business that has an address that's in the city of Toronto. So that's one way of graphically representing it. Notice I've left out the ands and ors in here. So this knowledge graph is incomplete in terms of capturing this definition. But in the world of ontologies, we don't just use the graph. We have that second level I showed you earlier, which is the actual definitions. And so this is a simplified use of logic to represent explicitly the definition of a Toronto resident. Toronto resident is a subclass of resident and resides in Toronto or owns property in Toronto or operates a business, and that business has an address, and that address, that the value of has address is an address where its property in city has a value of Toronto. So now we're getting much closer to the explicit representation of the definition of a Toronto resident. And if you want to see it in the actual logical language, this is typologic, description logic, and this is what that looks like in description logic. So as I said, an ontology provides you with the language with which we can define the semantics, we can define the meaning of classes, and impose constraints on their interpretation. Now, what does the ontology provide us with? The definition of Toronto resident is actually specific to the city of Toronto. This is not what the ontology is providing us with. What the ontology is providing us with is a set of properties: resides in, owns property, operates, has address in city, resident, address, business. It's providing us with a core set of properties and concepts with which we can now construct a definition of resident, whether it be in Mumbai, Beijing, Toronto, etc. And if we go to the microtheory level, within the world of description logic, we also have the ability to represent rules where we can capture statements like, for each year above the age of 14, a member of the household will leave with a probability pH. So how are these ontologies used? They're used as an interlingua. They're used as a means of communication across different systems. And they also can be used as a core representation of an information system. It's used for automated classification. We already talked about it being used to classify automatically whether somebody's a resident. It can be used for deduction. If you are a resident, then you can deduce things about being a resident as to what city you live in. And it can be used for model checking to validate whether what's in the database conforms to the definitions that are in the ontology. So we've talked about the issues that cities are facing. We've talked about that the sharing of data is a challenge for a variety of reasons. One of those reasons I mentioned was semantic interoperability. And we've now talked about ontologies as being a way in which we can achieve semantic interoperability through the explicit representation of the semantics, the meaning of the concepts, properties, etc. in the data. So now that we have the tools to address the issue of semantic interoperability across the silos in a city, how can we get cities to adopt this type of technology? One route is the standards route. So I've been working with, I'm a member of Working Group 11 on Smart Cities, which is part of the Joint Technical Committee of the International Standards Organization and the International Electrotechnical Commission. And I just want to say that the work we're doing with the City of Toronto is based upon the standards that we have been building as part of Working Group 11. Within Working Group 11, there's one set of standards I want to point out, which is the 5087 series of standards. That standard, it's a set of standards that are stratified. The lowest level is a foundation level of basic representations, an ontology of time, location, activities. The second level is citywide ontology. These are concepts and properties such as household, services, residence that can be both read and updated by multiple services. So at the citywide ontology level, we're talking about concepts that are used and altered by multiple services within the city. So if we're looking at households, housing may update the information about households, public health may update information, shelter may update information, etc. And then at the next level is the service level. And the service level is a set of ontologies where the data defined by these ontologies can be read by multiple services, but only updated by a single service. A good example are the transportation system, the transportation department. They would make available what the transportation network is. Other departments' services can read it, but only the transportation department can update it. So 5087-3 is the transportation planning ontology standard that we are creating. And then there will be additional standards in, let's say, water and sanitation, education, public health emergencies, etc. This is just to give you an idea of the different patterns of concepts that exist in each of these standards. 5087-1 covers things like activities, agreements, location, organization structure, provenance, etc. You'll note that in blue here, what we're doing is reusing existing standards, whether it be OGC, GeoSparkle, or W3C organization ontology, etc. So we reuse within the 5087 relevant existing standards so that we're not recreating the same thing. At the city level, we have concepts dealing with buildings and bylaws, the administrative structure of the city, contracts, households, indicators, infrastructure, land use, persons, extensions, city organization as opposed to just organization, etc. 5087-3 for transportation planning includes parking, transportation systems, transit, trips, trip costs, etc. And 5087-4 on public health emergencies deals with medical activities, resources, vaccination, public health events, etc. So in order to get these ontologies into use at cities, the path that's being taken is to embody them as standards within the standard development organizations and get them into use. So what I'm going to do is I'm just going to skip over the last set of slides because I'm running out of time, and I do want to take questions if there's any questions. But I do want to say one thing. I did mention in my abstract machine learning in smart cities, and what role pose the question, what role can ontologies play in machine learning? The bottom line is that machine learning is dependent upon an adequate representation of the domain in which the learning is going to be done. And the whole purpose of ontologies relative to machine learning is to identify, name what the entities are that you want the learning to be done over, what the attributes are that you want learning to be done over, prioritizing them in some way so we know what's important, what's not important. and linking these attributes in a graph, in a graph. So what the ontology is providing a graph representation to be as input, used as input to current day machine learning algorithms. There's been a lot of work within the OBO area, the chemistry gene area in using ontologies, and a number of technologies created that can transform a definition in the ontology, including the axioms, into a vector that can be used by machine learning to classify instances. And there are a variety of algorithms there. But there's a whole world out there of graph neural nets, which take as input graph structures and use as a basis of learning. So I'm going to stop there because I at least want to see if there are any questions. And so if there are any questions, please put it into the chat.
I think there is one question in the Q&A box.
Oh, there we go. I'm sorry, I had it in the chat. Yeah. Okay. So the answer is simple. There's
I'm sorry, but people wouldn't see the question. Can you read out the question just so that everyone,
sorry.
Yeah.
The question is regarding privacy. What is the scope of masking for maintaining anonymity of individuals? So in what I presented, there's no desire to maintain anonymity of individuals. The concept of anonymity does not apply when a city is providing services to individuals. So we can't have anonymity. We need to know exactly who the individuals are, who the households are, who you're providing services are, what their characteristics are. So there is no anonymity within the process. And the participants in the process only provide the minimum amount of data necessarily required by the process. Okay, any other questions out there?
I think there is one more, or two more actually, in the Q&A box.
Let's see. Are there certain things within a city that can't be represented by ontologies? Oh, we're getting a lot of questions now. It's a good question. You don't need to use ontologies to represent things like sensor readings. So, images, sound, sensor readings, etc. Aren't represented using ontologies. It's only when we want to make the transition from a signal or a numerical representation of those signals, etc., that we begin to introduce ontologies. How do you see the private sector getting involved in smart city revolution when it comes to ontologies? It's a good question. What's happening in the services sector, or what is referred to as urban tech, is that each one of the urban tech companies has its own data models. And what they suffer from is lack of adoption of a shared data model. That is, lack of adoption of a shared ontology. So let me give you a good example. At the beginning, Somya had mentioned that I'm also founding director of the Center for Social Services Engineering. So we do a lot of work in the area of impact modeling. What is the impact that a social service provider is going to have on the people that they're dealing with, on their clients? And what we have done is we've created an ontology for representing impact models, who the stakeholders are, what the outcomes that you want to achieve, what the indicators are for measuring the outcomes, etc., and also for reporting on the application of the impact model. And what that ontology is being used is as the interchange format amongst the different urban tech companies, amongst the software companies that provide software to the social services sector. The goal is to use this ontology as a basis of communication amongst the different software platforms. So for example, there's probably about 10, 20 different companies that right now are modifying their software so that they can both input and output impact information, impact models, and reporting on impact using this standard, if you will. Now, it goes further than that because now Microsoft and Salesforce is aligning their data models that they have so that it conforms to the common impact data. It's called the Common Impact Data Standard. So they're now aligning with it so they too can map into it and use that to exchange information amongst the different platform software systems, etc. So there needs to be a movement towards the adoption of these types of ontologies by these urban tech companies, not to replace their internal representations, but to be the language of communication amongst different software platforms so that they have a shared understanding, a shared semantics, so that they can achieve semantic interoperability. Okay. How is change management with regard to city policy formation used for impact and risk management in the scope of ontology? Oh, that's a tough one. I'm not sure that I understand it completely. If you can type in a little more elaboration, please do that. I'm going to go on to another question. So another person says, I'm thinking like the characteristics of the neighborhood can be so dependent on complex cultural and social factors. Absolutely. That is certainly the case. So I often say to people that working with cities or building solutions for cities is not rocket science or not brain surgery. It's much more complex. Rocket science, you're able to minimize the number of externalities, whereas in a city, it's all about externalities. Cities are extremely complex systems. They're extremely complex systems of systems. And as you point out, cultural, social factors, et cetera, play a major role in these. And so the only hope we have, and this is really why ontologies are important, is to be able to represent as much of this richness as possible in the systems that we use to address the needs of the citizens. And let's see, what is my take on data fabric? Well, I don't know what data fabric is. That's a term I don't use. So I would have to go and get the definition of data fabric in order to give you my answer. Okay, I think we're at the end of the questions and we're at the end of the time.
Yes, I think so. Thank you very much for this great seminar. We could see from the number of questions that everyone really found it interesting. Thanks a lot, Professor Fox. I also like to thank our colleagues at the University of Seoul for co-hosting this seminar series and thanking everyone who participated today. We hope to see you in our future events. We have a number of seminars scheduled for the following weeks. Please check our website for those. Thank you, everyone.